Thank you. I thank the organizers for the invitation. It's a pleasure to be back after 2 years of isolation. So today I'm going to talk about zero-point photon scattering in real materials, okay, since that's the focus of the conference, and some lessons and takeaways from our new Casimir force measurements, precision Casimir force measurements. Of course, my name is Umar Mohideen, and I'm at UC Riverside. First, I need to thank the people who really did the work. That's my postdocs and students, Banashev, Mingyu Liu, Jun Zhu, and Yuanzong Zhang, and the people who did theory. We just heard from Galina Kunchitskaya, who talked extensively about the theory. So, why do we do precision measurements of the Casimir force? You know, some of us are condemned to do it, right? And you know, when you start trouble, you got to keep repeating the trouble. Okay, much to the frustration of the graduate students. But that's just facetious. In reality, there's some real questions to be answered. You know, kind of questions is, are there any new physics? You know, is there anything, something that we don't understand here? You know, are there differences in how photons scatter, real photons versus zero-point photon scattering from real materials? No, that's a question that we can answer by increasing the precision of the measurements. And there's some fascinating geometry dependencies we heard from Jeremy and others, okay, which I will not be going into today. And others like, you know, we have optical thermal effects, which we heard a lot of talks on, novel materials, which, you know, is a frontier still left, you know, what you can explore, repulsive Casimir forces and such with materials. Okay, lots left to do. Okay, so what do you get out of making a precision Casimir force measurement? You know, if you can make improvements in both theory and experiment, and you can make a robust comparison of experiment and theory, and what you get out of that is, you try to understand how good is the general theory of the Casimir force when applied to real materials, okay? Not ideal materials, real materials. And how good is our understanding of the input parameters? If you're going to compare the theory to experiment, you have some experimental input parameters. How good is that? Okay, so this has been done a few times here already, but I just remind you. Of course, everything's based off the Lifshitz theory when it comes to real materials. And you start with Maxwell's equations of fluctuating E and H fields from the zero-point photons. If it's only zero-point photons, so it's thermal photons, we have to take that account thermal photons as well. And you have to use the fluctuation dissipation theorem. And here, it is the imaginary part of the epsilon that's critical in the fluctuation dissipation theorem. So, you know, this is something that we have to worry about as we compare the two. Okay, and we went through this already many times again. And the pressure is given in terms of this reflection coefficients for the TM and TE modes, and everything. The permittivity is expressed in terms of these Matsubara frequencies, and I want to bring your attention to the fact that you use local permittivities. It's only a function of frequency, okay, when we input it, all right? And that's part of the theory in the Lifshitz theory right from the start. And you can pick up the ideal Casimir result if you do, I think I skipped a slide here. You can pick up the ideal Casimir result in the terms of when you go to zero frequency at far separations, the two reflection coefficients go to 1, and you can get the ideal result. But now you have to put real parameters for real materials. And you can do that from the tabulated values of the refractive indices and calculate the permittivity from that. And when you go to zero frequency, the zero Matsubara frequency, which critically dominates at large separations, you have to extrapolate the data using the Duda model, which is the right description of material behavior, which is they have a relaxation parameter, it's an imaginary component, which comes from the photon scattering. It has to be in there. But the problem is when you go to large separations, zero Matsubara frequency, the TE mode goes to 0 for real materials, which means you get only half the contribution to the Casimir force. Okay, so the Casimir force goes to half when you put a real material in with this description, and which is what Galina was alluding to earlier. And you get a large monotonic thermal correction, which you can check for experimentally, even at short distances. Okay, so you don't have to just go large distances. And then there's entropy issues, which Galina alluded to already. So how well do we so the key question is, how well do we characterize the electromagnetic response of the material to the 0-point photon scattering? Okay, and are there differences between experiment and theory, either due to unknown systematic errors? The experiment could have systematic errors that we don't know about, or you have the wrong input of permittivity, because it's a critical parameter you're putting in when you compare theory and experiment. You could have the wrong permittivity into the theory. And you can solve some of this puzzle by trying different materials out, okay? And which you can use the material permittivity from tabulated data for the permittivity and the permeability, and for different materials, and compare, and which is what we did over the last few years. So the kind of materials you can compare is you can do the normal 2, which is gold sphere and a gold plate. You can then switch it to nickel sphere and nickel plate, which is magnetic. So you've got to worry about the magnetic response to the magnetic fluctuations. Or you can switch one of them to be non-magnetic. The sphere is non-magnetic and the plate is magnetic. And then make a comparison and see and look for systematic errors that you might have missed. Okay. So, and all of these, you have to input a permittivity, and there's 2 options. You can put the Drude permittivity and extrapolate to 0 frequency, take the tables and extrapolate out, and then you have this relaxation parameter for gold and nickel. You can just get that from the tables, or you can compare it to when you drop this relaxation parameter, okay, as we've been doing for years now. Okay, for permeability, you can again look it up, but permeability drops to 0 at very high frequencies, drops to 1 at a very high frequency. So, but low frequencies, again, you can take it up from the tables. Okay, so this is just a recap of old experiments. So Ricardo presented some even for longer distances last time, yesterday. So here's the data of the crosses, and the red line is a plasma model, and it's up to 300 and up to 500 here. And again, the error bars are the crosses, and the size of the crosses are the error bars. So, and Decca talked about other experiments as well. And you see that the data falls only on the plasma model, okay? There is an experiment from the Yale group which shows that the data falls on the plasma model, falls on the Drude model, but like as Ricardo said, the electrostatic force there was left to be hypothetical, and the electrostatic force, this hypothetical electrostatic force was 10 times the Casimir force, okay? So this is an issue, that it falls on the plasma model and not on the Drude model, and that's a problem, okay? There's a solution to this, and solutions were proposed, okay? All that you have to do is, since you're measuring a higher force than predicted by the Drude model, the green line, all that you have to do is subtract out some systematic error, okay? And this should agree. The possible systematic error, gravitational forces, is too small. The possible systematic errors are electrostatic forces. You could have electrostatic forces, absolutely true. And there's been a lot of nice work on that. And the kind of electrostatic force you expect is, if there's impurities on the surface, for example, you get potential differences on the surface, and the electrostatic force will have not just a monopole term, it'll have the dipole term and quadrupole terms, which will give you a curvature to the force. But the key point here to take away is, there's a specific curvature to the measured experimental curve, okay? So if you want to get an electrostatic force, there has to be a particular distribution for every different experiment. Will have different distributions of the patches. You got to have this correct distribution if you want to mimic this curvature and subtract it out identically. That's a problem to start out with, okay? So you just can't come up with any electrostatic force. All right, so then when you go to a magnetic plate, the problem gets even interesting. So if you use a magnetic plate, now again, the measured crosses are here, and that's the size of the error bars. Here, because the magnetic force contributes a repulsive term to the Casimir effect, the magnetic fluctuations, you get it lower, okay? So the Drude model is about, and this for different separation, 280, 350, all the way up to 540, and the error bars. You always fall on the plasma model curve, even for magnetic materials. But here it's lower. The electrostatic force is an additive force. It always adds, it always increases the measured force. But here, the measured force is lower, so there's nothing to subtract. It gets even more interesting if you go to, I told you already this, the electrostatic force is always additive, and you cannot subtract it. It's only going to lower the measured force. It's even more interesting if you have one magnetic material and one non-magnetic, which is a gold sphere and a nickel plate. Then what you see is that the measured forces fall both on the plasma and the Drude curve for these separations. Okay, so there's no distinction here between plasma and Drude. So this is very interesting because I can summarize this here. So when you change materials out, non-magnetic and magnetic, you see the following. So in the first case, when it's both non-magnetic, the measured is on the plasma model, which is higher than the Drude model. So you think you can subtract something out. So you can make green go to red. In A, you need to subtract. But when you have one magnetic and one non-magnetic, both of them fall together, okay? And you can't subtract any electrostatic force and get anywhere because it's already good. And when you have both magnetic, the measured force falls below. You can't subtract anything from your electrostatic force. So you can't reconcile the material dependence and get, systematic error, which is consistent with different materials, okay? And this was done, Ricardo did an experiment which, showed that the thermal dependencies are ruled out by a factor of 1,000 for the same reason, okay? So that's this difference force measurement here. So this is a puzzle, okay? And the puzzle is, you can't consistently subtract systematic errors and get experiment and theory to agree with the Drude model, okay? The experiment so far for these separation distances is always in agreement with the plasma model. But here's a puzzle. You can't leave out dissipation. The whole theory is based on the fluctuation dissipation theorem, and you can't arbitrarily throw out dissipation for some frequencies and claim that you got agreement. That's deeply unpleasant. Okay, so you can't just throw out dissipation. So this is a puzzle. We have to figure out what we're going to do. So a couple of things, and Ricardo alluded to this before. Maybe all this is happening because we are only at short separation distances, up to a micron. So maybe we will see changes if we go to large separation distances of 1 micron. This is just fortuitous that agrees with the plasma model, short separation distances. Again, number 2 problem is, maybe we're just going about the whole thing the wrong way, because we are using only local permittivities, because the tabulated data has a refractive index as a function of frequency, which means you calculate the permittivity as a function of frequency. But we know fluctuations are not, just local. Fluctuations are non-local. The epsilon has to be both a function of k and omega, which is to say they are fluctuations by definition. Quantum fluctuations, they're off the mass shell. Omega is not equal to kc. You can't always deal only in the limit of omega being equal to kc. You have to go off the mass shell. You have to integrate the k separately from the omega, okay, when you calculate the response function. Okay, so we can do this. 1, we go to largest separation distance. Ricardo has done 1, and I've done 1. And use different materials, again, to tease out, how to address this problem. Okay. All right, so the first one we did, we started a few years ago, and we made a factor of 10 improvement in our precision and measured separations up to 1.3 microns, and actually measured longer distances, but we reported up to 1.3 micron, and I'll tell you why. And the way it was done is we also tried to address the fact that is how to get rid of the patches. We use argon ion cleaning and UV beams to get rid of the patches as much as we can. We go to high vacuum, ultra high vacuum. And this was a minor problem, it never was an issue, but we decreased the surface roughness issues. And then we compare theory and experiment. We do it the same way. We look at, we look at the frequency shift of the cantilever because of the interaction force. We just model the cantilever as a harmonic oscillator, which means that in the linear limit, we can only do distances larger than 200 nanometers. And the kind of things we did improved is we made the spring constant of the cantilever softer, much softer, by taking a cantilever and chemically etching it to make it thin, effectively, reduce the spring constant. And then we put a hollow glass sphere. We put a very hollow glass sphere, so this is very light and can hang on the cantilever, and then coat it with gold and repeat the measurements. Give us a factor of 10 improvement in sensitivity. Now, the key thing is try to reduce the patch effect and go to a higher vacuum so you keep your surfaces as clean as possible. Okay, you cannot do this if you do surface physics, which you do ultra-high vacuum, 10 to the minus 10 torr, you usually bake the chamber to get rid of all the impurities in the chamber. We can't do that here because we've got a cantilever and thin coatings on the material. So the cantilever will just completely, as people who do thermal physics know, the cantilever will completely curl up. So we can't do that, so we had to come up with this other way of doing it, use an argon ion beam to clean the surfaces out, and a UV beam to clean the chamber out. Okay, two things we had to introduce. And then we can get to ultra-high vacuum kind of pressures, keep everything clean for long, and make a long time frame measurement. So here's the argon ion beam. Will clean away all the impurities, but then the chamber still has a lot of impurities, so you have to use a UV light to clean the chamber out and repeat it over and over again. As you clean the chamber out, everything will come onto the plate, you clean the plate out, and you go through a cycle of this, and you have to learn how long to do each one, and it takes a while to figure it out, but in the end you can get there. So we get ultra-high vacuums, clean, pristine surfaces, okay, and the potential difference of surfaces can be got to zero. The electrostatic force can be almost negligible, for separation distances that we're talking about. We do this. So here's something, if you, before cleaning, the potential difference as a function of separation, you can see it has some non-monopole effects, dipole and quadrupole. That means the potential difference is changing as a function of separation. You can see that, but it's fine. It's very small here. It's before cleaning, it's negligible. But once you do the cleaning, you can get it flat and the potential difference to be almost zero. You can eliminate all the electrostatic effects and make it negligible. So that's one advantage you get from these kind of cleaning procedures. Okay, and the roughness I told you, it's already very small. We were able to reduce it by another factor of 2. So here's the measurement setup. So we have oscillating cantilever whose resonant frequency changes because of the interaction force, which we measure the one interferometer, and the second interferometer to measure the how much the plate moves close to the sphere. But one thing is we have to absolutely calibrate the separation distance. So this gives you the relative separation. We still have to come up with an absolute calibration. And we do this at ultra-high vacuum pressures. Okay, so same thing we've been doing for years now, which is you calibrate the system by applying different voltages, very small voltages, and you draw these parabolas at every separation because the electrostatic force is a parabolic function of the voltage differences, where this is treating it as a monopole, so you have to verify that's a monopole, that's a constant potential difference as a function of separation in all calibrations. Okay, that's always an issue. If you don't, then you start fresh again with a fresh plate and a fresh cantilever until you get that to work. Okay, and the absolute separation distance you get from and the spring constant you get from the couch or the parabola. That's these terms here. Okay, so important check is this calibration constant, the absolute separation distance. Here's the couch or the parabola as a function of separation. You fit different sections of it and make sure that you get the same value for all the separation distances. Okay, so if it does not true, that means you got some systematic errors that are mostly electrostatic. Same thing for the spring constant. You got to check whether that the spring constant, effective spring constant C here, doesn't change as a function of separation distance. Okay, and then when we do this, we get this is the result, and this is as a function of different separations. This is up to 400, this is up to 600, 950, and 1300. And this is a Casimir force gradient as a function of separation, and you can see the error bars are there, but it's too small for you to see there. It always falls in the plasma model. And you can see as it gets to larger distances, the mean value is slightly getting off the plasma model, okay? But we stopped at 1.3 because the error bars are so big that the error bars are overlapping the Drude model as well. You can go out, but the mean value is always closer to the plasma model. Okay, it's never goes to the Drude model. The error bars are bigger. We can go as we explored, but it's also going a little bit off the plasma model. So it's not as you go to larger distances. We can tell maybe the agreement with the plasma model at short distance is fortuitous, maybe, but it's always in better agreement with the plasma model. Okay, the plasma model is the only thing that agrees all the way up to 1.3 micron. It's clearly off the Drude model all the way. Okay, there's no agreement with the Drude model at 1.3 microns. But so the experiment agrees with no dissipation plasma model. Okay, for these separations, okay, and disagrees with the Drude model. This is a problem, okay? We can't be throwing out the imaginary part, okay? But that's what the experiment is saying, and Ricardo presented his more recent experiment yesterday. Same thing, okay? It only agrees with the plasma model. So what do we take away from this? So even after increasing the precision, eliminating the role of impurities and any surface impurities and electrostatic patches that might have, there's a disagreement between experiment and theory, okay? So now we have to go to possibility number 2, okay, which is maybe our input parameters are wrong, okay, which is that we are doing only the local permittivity from the tables, and the tables have only the local permittivity, okay? So maybe that's where our problem is. But how the hell do we do now get better at this? Because we can't, because all the tables have only the local permittivity. All the tables use real photons to measure the epsilon, either, you know, ellipsometry, reflection, you know, all the time you're using real photons, which are always on the mass shell. Omega is always equal to Kc. That's why epsilon is only a function of omega. Right? So how do we come up with a non-local permittivity, and how do we then put that into theory and get a better agreement? Okay, so that's what led us to, we got to go to different materials where we can get the non-local permittivity and non-local response of the electromagnetic material to the electromagnetic fluctuations. And that was our idea to go to graphene. Okay, so why is the Casimir force from graphene interesting? The complete electromagnetic response can be calculated from first principles. So you can get epsilon as a function of K and omega, not just omega. Okay, and it has some interesting Casimir effects in itself. For example, it has a very because of zero band gap, it has very large thermally induced fluctuations, and a lot of theory on this. Okay, let me see if I have, yeah, a lot of theory on this. Okay, and this is only a partial list. So the thermal effects in graphene are very large and can be observed even at very small separations, because normally in metals you got to go to very large separation to observe thermal effect if you're using the you know, in all the experiments, and if you use the plasma model in particular. And the reason that the thermal effects are very large in graphene is in pristine graphene you have zero band gap, so small thermal temperatures can excite these quasi-particles, which are relativistic and massless. Okay, so you have large fluctuations in graphene, so you have large thermal effects in graphene, and it can be a factor of 10 to the 7 higher. Okay, so it's very large, so you can measure these thermal effects in graphene, so it makes it interesting in and of itself. Okay, so I already told you some of the improvements that we did, and we went ahead and in sensitivity that we implemented for this experiment as well. And a couple of key things we did for the new experiment on graphene is we independently measured the, we removed uncertainties from the carrier concentration of the substrate. I'm going to tell you that in a little bit. But we also independently measured the band gap of the graphene, because we're using real graphene, not pristine, not ideal graphene, so it has a band gap. And we measured that using scanning tunneling spectroscopy. And we did an independent determination of the impurity in the graphene as well by using Raman spectroscopy. Okay, so in a previous experiment, when we did this about 10 years ago with graphene, the error, which we did not realize when we did the experiment, was, as everybody was doing in those days, you put the graphene on a small, 300 nanometers of silicon dioxide. This way you can see the graphene, okay? And then below that, you always had silicon. In this case, it was boron-doped silicon. And the carrier uncertainty, the conductivity uncertainty of the silicon, because of the doping, meant that we had a big error bar in our measurement, and that was a problem. So we could not tell that we're seeing the thermal effect of graphene when we did no experiments. So in the latest version of the experiment, what we did was we got rid of the silicon, okay, and made all SiO2 now, and then put the graphene on top and repeated the measurement, okay, with the higher sensitivity system that we now have. So we put the graphene on 500 micron thick SiO2. Of course, the SiO2 has negligible conductivity and very low Casimir force, so we eliminated error bars associated with that. And spheres, typical spheres that we use, the hollow glass spheres of 120 micron. Okay, we determined the band gap of graphene by using scanning tunneling spectroscopy. So this is the differential conductivity as a function of the bias voltage, and by extrapolating these two sides, we can get the band gap. Again, it's not pristine, that's why you don't see the triangle, you don't see the cone, okay? You see a parabola instead, because of the impurities. Okay, and then we measure the impurities by using Raman spectroscopy. The triangles and the solid line here is literature tells you how the G peak, the Raman peak, G peak varies as a function of concentration, impurity concentration. So these are the measured values. We just go different points along here and measure the G peak, and from that we predict what the impurity is, and this is a impurity profile on the sample we used. Okay, so we can tell what the impurity concentration is just 10 to the 12, which was surprisingly high. We were hoping to get much less, but that's what it was. It was too high for our expectations, because last time when we did the experiment, we had a much lower value for the impurity concentration. Okay, so so we measured the Casimir force using the same technique. Okay, so I'm not going to go into detail on this. Okay, but the key point is, again, you always, here's a potential difference between the graphene and the gold sphere. You have to make sure that it does not have, it's constant as a function of rate field separation. Otherwise, you can't do the experiments because you can't subtract out any electrostatic effects with high precision. Okay. And Galina has already covered this. We use a polarization tensor approach, which Galina talked about already, to compare theory and experiment. And here are the results. And yeah, we have a lot of time. I think I went too fast. So here's the force gradient as a function of the sphere plate separation. There's up to 200, 300, up to 400, 500, and 700. And the crosses are the data, which are the size of the crosses are the error bars. And you can see there's two bands here. The red band is a high temperature. The experimental temperature is 294 Kelvin. The blue one is a 0 Kelvin. Okay, and you can see the data is about 0 Kelvin, telling you the thermal effect in graphene. Okay, so we can easily see the thermal effect all the way up to 700. That's why we stopped the data here, so that we can see the thermal effect after this. Okay, and the reason we have bands is the red band, the top line and the bottom line of the red band tells you the errors in the theory because of the errors in our impurities. Because we had a high impurity concentration, we have errors from that, which comes to the band gap and the chemical potential. Okay, so that's the error. So the errors are reflected in the theory errors are reflected by the band of the red band and the blue band. Okay, so within these theoretical errors, we get very good agreement for the Casimir force from graphene as a function of separation distance. So the key point is the thermal fluctuation can be easily observed now finally in graphene. Okay, and this theory, even though we're using a gold sphere, it's independent of the zero component of that's a Drude plasma problem, because graphene is so thin, the reflectivity for graphene is small enough that it doesn't matter. It's a very small difference whether you put Drude or plasma. It doesn't matter. So that complication we eliminate altogether by using these different materials like graphene. Okay, so so just to conclude this one, so the nice thing about graphene is we have the complete electromagnetic response of graphene can be calculated from first principle. So epsilon is a function of K and omega. Graphene is interesting because of the very large Casimir force, even though it's an atomically thin and has very large thermal fluctuations. That's what gives you the large Casimir force. Again, we use the same dynamic AFM technique to measure the Casimir force from graphene. We characterize the impurity concentration and the band gap independently to make sure we get our theory input correct. And the experiments show good agreement with the first principles PUD polarization tensor theory with no fitting parameters. Okay, there's no uncertain parameters here. Okay, so final conclusion. So what do we get from all of these different materials? Okay, the takeaway is the current understanding by comparing precision measurements of non-magnetic materials, magnetic materials, and graphene. Okay. So use an experimentally determined local permittivities, which is what we get from the optical tables, and mu of omega, which always involves on shell, omega equals Kc, fluctuations. Our potential errors in applying theory in the case of normal metals. Okay, and this is so it goes for Ricardo's experiments and other experiments as well. You know, we always get disagreement. Okay, when you put real material properties into calculating the theory from the Casimir force, theory of the Casimir force. Okay, so we really need to go non-local. Okay, off mass shell to calculate the 0-point photon scattering with the real materials. But this is a problem because we always have to use, there's no way to experimentally determine off mass shell behavior. Okay, you have to only, maybe phenomenologically, we heard Carsten and we heard Raul, you know, many of you have done, try to figure out what his non-local contributions would be. But it's all phenomenological. Galina talked about some of this earlier. But experimentally, there's no way, we haven't come up with a good way of coming up with a non-local permittivity, and which you can input into the theory to get the right theoretical prediction. But we have materials which are Dirac materials, graphene being one of the best studied, and there'll be others, and there are others, and there'll be many soon, which will avoid this complication. So if you do it with the Dirac materials, we can always calculate out what the full non-local permittivity is, the off-shell mass, the contribution of the off-shell mass components are, and then come up with the right theory, which we can be confident about, and then make a precision measurement and compare, and we'll get a better understanding. Thank you.
Questions?
Thank you, Umar, for a great talk. So are you sure there isn't some experimental way to try to measure epsilon, omega, and K? I mean, it would seem like...
I don't know. I don't know.
I agree. It's hard to see.
You know, because it's by definition, you're off mass shell, right? You always use real photons, shoot it at it, do ellipsometry.
Maybe there's some other indirect way, you know, independent of measuring Casimir forces, another handle onto that thing where this would come into some fluctuation phenomena or something.
I don't know. I mean, I don't know if Carsten's looked at, I'm sure, I mean, people working on this have to come up with a way of checking your theory. I'm sure you looked into what experiments are there. I don't know.
Keywords, anomalous skin effect.
Okay. Now,
but this is not the only possibility.
Yes, there's one maybe that'll contribute a small part of it. Yes, the anomalous skin effect.
But you can have a look at. I mean, there have been experiments along these directions for the anomalous skin effect. But you can go. There are other phenomena that you can look at.
You can look at each phenomena separately and then add it all up together to get the whole K omega dependence, because I know Raul did something with this.
Yes, this is the great work. I mean, Raul was with Vitali was one of the first that were saying about the anomalous contribution of non-locality in the Casimir force, and they were also pointing to the anomalous skin effect as a possible source of modifications, and they were saying, have a look at that.
Yeah. But I guess the conclusion was from their work is that it's too small to make the difference up.
Well, the point is that it depends on the model, of course, right? So it really depends on the model that you are considering, and there are a lot of models that you can have a look at. And at the moment, all the models that have been considered in the theory provide a contribution which is small, that in order to fill the gap between Drude and plasma. But this does not mean that it's not possible to have a check. And there have been experiments that are investigating this region, and that there are other phenomena which are related with that.
Yeah. So yes, I absolutely agree with everything you said. There's no easy handle, is what I was trying to tell Kim. You know, to do one experiment and get the whole difference up. You know, predict what the absolute K is.
Because we are used to think in terms of spectroscopic terms. So you just shine laser and then measure the optical response. But this is not the only way of measuring the optical response of a material, right?
Absolutely true. Yes, you can piece it together. Absolutely true. But so far, there's not enough literature out there to piece up the differences.
I will look in the material science. I don't know if there is not a lot of literature of that. I mean, the people have been working on this kind of things. I mean, in material science, there's been a lot of work on this kind of things. And yeah, I will probably look at there. But again, measurement on the anomalous skin effect have been done already in the 70s.
Yeah, anomalous skin effect has been done, but that was too small, as I understand.
No, well, this was the contribution to the Casimir force, but
Yes.
the measurement of the anomalous skin
Yes.
effect independently from Casimir
Yes.
has been done by looking at total internal reflection, for example.
Yes.
So you can use also grazing wave incidence in order to measure the evanescent region.
Yeah. Yes.
And also with spectroscopically, you do the same. You do shine a laser, you look at the optical response, and then you assume that your reflection coefficient have a Fresnel formula, and then you do ellipsometry in order to infer the epsilon. So
Yes.
to some extent, it's also an indirect measurement of what you're doing there.
Yeah. So yes, you can piece it together and try to get a complete K omega dependence, and then check again. Okay. But also the fluctuations, photons itself are also intrinsically of mass shell, so you have to take that into account as well. Both the response and the fluctuations are both off mass shell, and you have to take both into account.
Yes, but
Yeah.
okay.
Yeah.
Yeah. Can I have a remark over here. So item number 2 here on your slide, it says epsilon of omega k and mu of omega k. So there is a theorem in electrodynamics of continuous media that says that having epsilon a function of omega and k is equivalent to having magnetic permeability.
Oh, okay.
So you don't need
Okay, I
to
know
include
it's
K
separately.
in mu. So it's either epsilon of omega and K, and mu is equal to 1 then, or epsilon of omega plus mu of omega.
Oh, okay.
These two ways are equivalent, and that was previously elaborated by people like Agranovich,
Okay.
quite big people there. There are papers there. I can send you the references.
Okay, great. Thank you.
Umar?
Yeah.
Quick question here. Hi. So it seems like a lot of the interpretation depends on precisely knowing the gap size. So how well do you know that in these measurements? Like a little lateral shift in the plot seems to be the source of most of the
so that's why you have to determine the separation distance independently.
So how well do you know it is?
Okay. Very good question. I'll show you. Usually to a nanometer, a fraction of a nanometer. Yeah. So that's how well, that's the separation distance here, you see.
Okay.
As a function of, so it should be constant at whatever section of the calibration curve you choose, you should get this flat. Otherwise, you can't believe your data.
So the other comment I had is, since the exact same fluctuation dissipation theorem goes into the thermal measurement, would a complementary measurement simultaneously done help resolve essentially whether there is agreement or the same disagreement in the thermal measurements also?
There will be
Right.
the fluctuations from the material dependence, right? I mean, not knowing the K dependence of epsilon. Yes, you should see. But how do you
if you were to do both the measurements simultaneously,
which is what you do if you do it at room temperature.
right?
So,
and if you measure the heat flux also,
the heat flux also.
then perhaps you can correlate whether the two measurements agree or disagree in the same fashion.
If you do the heat flux as well, and you can do it precisely enough, yes.
Thank you.
Umar.
Yeah.
So I already admire your experiment.
Thank you.
We're inspired by your sphere plate configuration when we did a thermal measurement, right? So
Thank you.
I guess these two communities don't come together often, so I'm going to ask a more controversial question. It looks to me, because I can work on force, right? You're trying to do as precise measurement as possible, and then begin to see the theory. But I get a little bit more trouble with the strategy here, because the theory can never, at least to my knowledge, you cannot be precise. Because now if you look at scattering, right, your damping term, you use a gamma, and even you take gamma from the measurement, right? Because when you deposit the sphere, the metal on sphere, or the gamma depends on grain size, depends on thickness, right? And furthermore, if we did another electron photon scatter, the gamma depends on frequency, right? So now when you go to graphene on silicon dioxide, you see graphene, you can do QED, but the surface photon polarions on the silicon dioxide will affect the electrons in graphene. So how much of those we know? We can't calculate those. So where then is the confidence?
Okay, good. That's question. Okay, yeah. Good question. So very good question. Yes, all true. But the problem is how you put the error bars on the theory now. So you can put error bars on the theory, like, based on what the relaxation parameter is, how it's changing, how much it's changing. So you get an error bar on the theory from that. And then you compare experimental theory. You don't compare, just put one value. So you have to put an error bar on theory, either from gamma, or in the case of graphene, from the substrate. Okay, you have to put those and then compare. But the important thing is how you get. We're not doing only one point. This is a nice thing about the experiment, because you're doing over a huge range of separations. There's a curvature to this behavior, and by putting these error bars, you can be generous in putting these error bars on the gamma or any other effect. You can decipher whether there's a whole scale problem or it's just at one point, because we're doing a whole distance range. That's where the advantage comes in of making a precision.
Which I agree. I think the distance dependence,
yeah,
it seems to me, based on the calculation, right? I would be really convinced if you measure the temperature dependence, because at least that say there is a region where it is flat and then the curvature up. I guess that's a much harder experiment.
Can you tell me that again? Can you repeat that?
Because the previous talk showed the calculation, the temperature dependence, right?
Yes, yes.
Right? If you do the temperature dependence measurement, because you're doing the surface effect.
No, yeah. Yes. Right now we can only compare zero temperature versus room temperature. You're saying do the temperature for different temperatures and make comparison. That'll give you a better handle as well.
Right.
No, absolutely.
Because the zero temperature is the calculation.
Yeah, the zero temperature is a calculation. Yes. Thank you.
Hi, very nice talk, and thank you for kind of explaining the kind of problems of the non-locality. Just had one quick comment and a question. So as another kind of member of the audience also mentioned, the problem of measuring the non-locality in the dielectric constant is a separate problem from the Casimir problem itself, right? And it's very nice to see how these two things are connecting. And just wanted to point it out is that other than the anomalous skin effect, like back in the 60s and 70s, there was a lot of work in actually measuring these non-local constants. So one example, actually the kind of solid state physicists were inspired from plasma physics, where also the non-local constant has been studied, is what is known as Tonks-Dattner resonances. So you take a very small thin film, if you do conventional ellipsometry, you'll only get a kind of plasma frequency which is independent of momentum. But now if you come in with light, you will see that the absorption occurs not just at the plasma frequency, but also multiples of the plasma frequency. And this can only occur if the plasma frequency has a momentum dependence. And from there, these Tonks-Dattner resonances, from there you can actually evaluate non-locality. And this is actually not a difficult experiment. It's the sample preparation which is extremely brutal to actually see these resonances. Now, going ahead to, let's say, 2020s, we have many new techniques like, say, microwave impedance microscopy, where you come in with a tip, you send in light or send in microwaves and try to understand the impedance, but now in the near field. So from there also one can get new insights into these epsilon omega k response functions. I agree with you 100% that this is extremely challenging to piece together all of these things. But I just want to mention that in principle, this is possible to solve with a lot of effort and this.
I would agree with you. Yes, it's hard to piece together, but my point being, that's a good thing to look for and piece together, because that might explain the difference. That's the, yeah. Okay. So that's the point. So, we should, and there are others, people are looking at it. Raul started looking at it 10, 15 years ago. So, people have looked at this, and we should piece together for different materials and then see what the non-local dependence is and see if that makes up for the difference. But the difference is real, and this is a way to look for the difference. Okay. Yeah, definitely can be done. Yeah.
A beautiful talk. You mentioned that the magnitude of the Casimir force is much bigger in graphene. Now, is the actual force you measure bigger, or is it just bigger
it's much
because
smaller.
of when you take out the thickness dependent? In fact, you only got a thin layer, so the actual forces you're measuring
is 10 times smaller.
It's the actual forces are 10 times smaller,
yeah.
Even though it's only normalized to a thickness.
But the amazing thing, it's an atomic layer. It's only 10 times smaller.
No, I understand that. So, what would you expect to see from graphite?
Oh, graphite. It'll be definitely less than a metal. I would say about 30% or so, just looking at from the dielectric properties of graphite. But depending on the thickness of graphite, of course.
Well, you might then be able to have your cake and eat it too. You might have a force that's big because you have many layers,
yes,
not just one.
Yes.
But then, so you might end up being able to use graphite to get a much bigger absolute force.
Yes, but then you have to know this epsilon as a function of k and omega.
Yeah, that doesn't make all this other nonsense go away. But it, just from an experimental point of view,
yes,
it might let you be measuring a 10 times bigger force with better accuracies.
Yes, but then you don't solve any, the thermal fluctuation, the thermal force is going to be small, it gets less interesting. Definitely it's worth doing, but it's less interesting.
I just want to make a comment and a reference to also what Redmond was saying. I think that the cross-fertilization between the community of Casimir and heat transfer is actually very valuable. And in particular, concerning the plasma Druta controversy. So first of all, simultaneous measurement of Casimir and heat transfer will imply that Casimir is measured out of equilibrium. So you have an out of equilibrium contribution to Casimir, which can be tricky probably to analyze. So Maura has done some work on that, could be interesting. But what is interesting is that there was a paper by Pierre-Olivier Chapuis, who was here a couple of the week before, where it shows that in heat transfer, actually the low frequency part of the S polarization, which I like to call, and we did some work with Carson on that, the eddy current contribution to the response function of the local material, it's actually very important. So if you can make a measurement of near field heat transfer and at the same time Casimir to check whether a model with non-locality is better suited in order to describe the experiment, it would be great.
Yeah, it's a tough one you're asking. Let me tell you.
I'm sure.
Because as people who make heat transfer measurements know, you're going for very high sensitivity or force sensitivity in a Casimir force measurement. There you're measuring the temperature difference. So they are kind of, the experimental requirements are not compatible with the techniques we are using. I'm sure maybe some of the
But certainly the people of heat transfer can provide probably better confirmation about the description of the model, because you were showing some beautiful measurement for metals, and we were showing that at short separation the behavior changes a bit, and this is essentially due to non-locality. Yeah.
Yeah. No, and that's critical because of the distance dependence. You have to show that you can measure, separation distances very well. Otherwise, it's pointless because we're depending on the curvature, right, to show the difference.
I have a comment about Professor Bishop's remark about going from graphene to graphite. Actually, if you go to graphite, then the low frequency optical response is different than graphene. It's just a different material. So you are not going to see these kind of Dirac-like features you see for graphene. Yes. In fact, I think the transition is something like 4 or 5 layers. So if you go further, the zero, as you approach the zero frequency range, for graphite, things are different than for graphene. So
Yeah.
you're not going to measure the same thing.
Exactly true.
Yeah.
Exactly true. Yes. Thank you.
Okay, let's thank Umar again, and we can continue the lively discussion over the coffee break, and we'll reconvene at 11.